Cool. Greetings. So, first things first. I see everybody brought their laptops. That's so cool. Is that because there's a deadline tonight? Yes, I guess so. How's it going? Oh my God. Don't give me that look, Glenn. That was, yeah. I need a bodyguard if I have that look. How is it going?
Poorly?
Poorly? Okay. Anybody disagree with that? No? I haven't even checked, but I will check now just in front of you guys just to kind of see how things are going. Let's have a quick look here. Let's just have a sudo bash. Find overflow, grab success. So, quite a few of you done overflow number one. A handful here, here. Oh yeah, all the names are here. Sorry guys. That was the plan. But anyway, nobody did overflow 3. One person succeeded number 4. What on earth is a fake success? It's not that I count the number of files called success, you know? Fake success. Okay, we'll need to talk. Okay, so it's going a little bit. Do you feel like you're learning? One person's learning? What?
Some of us have run into issues with 3 where we're just completely stuck.
I see, okay. Yeah, I like when people move into the third person. The future likes when people move into the third person.
Okay, me and others, how about that?
Yeah. A friend of mine, yeah, no, that's true. So they run into problems with 3. What's wrong with 3? What is the problem?
At least what I've run into. So we use farm build to put in a full-size shellcode.
Mm-hmm.
And we use the exact same shellcode as we used that worked in attack 1. Return to it, and then when we use it on attacking or overflow, it just ends quietly. It doesn't open a shell, it doesn't give any error message, no core dump.
Oh,
Yeah.
withers.
Don't really know where to go from there.
Huh, okay, that's something to take a look at then. Should I have extra office hours today? Would that be helpful? Would people show up for that? Let me see when I'm available. Of course, I'm recording all this. Calendar. No, that doesn't work. Here we go. Calendar. Yeah. 3:30 to 4:15. Is that okay? Because this is not materializing. Okay, 3:30 to 4:15 today. I have extra office hours. Okay. So if you guys have last-minute questions, which I suspect some of you might, we can go through that. One thing about overflow 3, so it expects you to have 2 arguments. It expects you to have a checksum, right? So in the middle. Is that something that's bothersome? Matching the checksum? How have people been tackling this challenge?
I changed. Do you want me to answer?
No, it's just this static expression of surprise.
So I altered the C file and recompiled it such that it prints out what the actual sum was. So I just changed my hex bytes to get a.
But then you're attacking a binary that you changed, right?
Well, so the actual return address I would have to get from the normal one.
Okay.
But I would just use that one to check what my sum was.
Okay, so you modified the original program to tell you what the checksum's supposed to be, right? Yeah, that's a good idea. So every time we can make a tool to make life easier, it's probably worth it, right? So having a little tool where you just like put in the arguments that you've been assembling, and all it does is print those arguments back to you with 1 extra character, which is the thing that will help you defeat the checksum. That would be a very useful utility indeed, right? As for why it's crashing, is it Pharma? I don't know, I haven't played Pharma. There could be a variety of different reasons, but we could try tracking it down. One good way of debugging things like that is, you have your shellcode, put in that \xcc, the int3 thing, just to see if it's actually executing your shellcode. And what you also see from there is that when you open your shellcode, is it in the right format? Did it get whacked by some internal process? You can even put it right before you can even replace int ox80 with just oxcc and see are all the arguments set up for it to use. Because one of the things that happens when these shellcodes is that if your stack pointer is at the same spot as your instruction pointer, then whenever you do a push, you're overriding a part of what you're executing. You're stepping on your own toes. So it's very important to have enough stack space. So if you just use vanilla shellcode like the one we created, where we use the stack excessively, you have to make extra space for the stack stuff. If you use the standard shellcodes like the one that does a jump and a call and so forth, you don't have to worry about that. Does it make sense? Okay, so any questions about the homework though? I'll let you have a few more hours left. Anything that was kind of particularly ununderstandable, or is it just kind of like a function of work and luck? Any questions? No, okay. Do you like more of these? Because I have a whole bunch more. I won't open it just yet. Let's give it a couple of days. But the next one is called Taunt Lab. So it's going to talk about some of these more esoteric approaches to exploitation that we'll be discussing today and that we've been discussing a little bit in the past few lectures. They're going to include something like this. Using the heap. What is a heap? Yeah. So far we've been talking about stack overflows, right? So when you have a program, you could put everything that you like on the stack. And in fact, our programming languages that pretty much only do that. But normally, when you're programming, you tend to want to have something around for more than just this local stack frame. You want to have a global variable of some sorts, right? Or you want to have a data structure that lasts a little bit longer. Yeah. Talk about the heap. The heap. In fact, this is the normal state of programs. Is that you're using pretty much always malloc or new or things like that to keep track of your variables. In fact, people don't really use the stack for anything useful anymore. So these stack overflows we're talking about, they're a little bit an endangered species. However, this stuff, yes, this is up and coming. Well, it's been up and coming for a long time. So let's talk about heap overflows, and I'll talk about two different kinds. One of them is a kind of slightly rarer kind, but just to kind of show you that things can fail in a variety of different ways. I want to talk about the static buffer it's being overflowed, and then we'll talk about malloc, and we'll talk about the intricacies of malloc. So let's talk about static buffer overflow. So suppose I declare a static buffer. Now, what is a static buffer in C? Do you guys remember this? If I have I've declared a function and I have a buffer called buff and it says static in front of it, or if I have it as a global variable, what does this instruct the compiler to do? It stores in a special section of the heap called the PSS, which is an area where your buffer just gets to live on and linger and have children, and whatever it wants to do for the rest of its life. It's always at this static location, which is what the keyword is referring to. It means that if I have a function with a static buffer, next time I call the function, the same stuff is going to be in the buffer. It's not going to be a different buffer. It's guaranteed to be there. It's really nice, actually. You can have a static int or something. You can keep counting as you get into them. So these things have global namespace. Now suppose that you have a buffer overflow in a buffer that is static. That means that I'm overriding what after I... The what? Yeah, override other stuff in the DSS. There's no return addresses, right? So it'd be easy to conclude that, like, well, no return addresses. Doesn't do a thing. Isn't that it? Who cares, right? But there's actually a lot of stuff on the static buffers. So here's a view of the program. If this is address 0 over here and we move upwards here, now remember we have our program here at 08, 04, and then we have initialized data. This is like the strings that are hard-coded into a program, or the initialized values you put into various things, or arrays and stuff. And then we have our uninitialized data, which is the BSS section, or static buffers that you're going to be using. It's right here. And then you're going to have a whole bunch of segments dedicated to malloc, which we'll talk about later. And then up here is the user stack. You remember the stack goes down, it goes up. Okay? So they can meet or whatever. Make sense? So, what can we override in this case here? There's a whole bunch of stuff. Okay? And these are going to be probably feel a little bit esoteric to you, but they're internal things that are being used by things like printf and scanf, and if you want to open up a directory like open3 and so forth, they're just internal types that are stored in there because when you call printf, it needs to manipulate the stuff that is printing out. And so it keeps a few static variables around. When you do open there, or you want to scan there, you want to, which means that you're opening up a folder, you want to see what files are in it. You want to keep some state about where you were. That state is kept in there. There's also RPC callbacks, window callbacks at exit. So if you're making, say, a GUI, normally when you're making a graphical operating system or a graphical interface, what you have is that you have a giant loop, and all this loop is doing is to be like, did something change? Did somebody like move the mouse or hit a key, or was there a packet that came from the network? So there's this giant dispatcher that then goes to say like, oh, there's a click on the mouse. Oh, no. Okay, so where's the mouse? Okay, it's right here. I'm gonna find what program is at that particular location, and I'm gonna tell it through an event that there was a click on its surface, right? So that's what this dispatch is. This is what Windows is doing all the time, what X Windows is doing, and so forth, right? So these callbacks, everything instruction types as callbacks, are the things that receive the events that we're dispatching through these types of event flow. Okay? So these window callbacks actually also live in VSS, in programs. RPC callbacks, same thing for a network. If somebody calls us, be like, hey, I have this remote procedure call that you need to be executing on your machine. Also stored there. So it's moved right there. At exit, little handlers that say like, should I be doing something special when I quit? For instance, should I be saving things to disk, or sending a signal to syslog or some system administrator when I quit? There's a little handler, a little function pointer that's near. Malloc has a special function pointer for debugging, like a hook. Catch and has its own environment table as a look there. It's called the EMVP, I think. Temp name, for getting temporary names. When we start the program, when we end the program, that's also something called CTORs and DTORs, and it's located right in there. So there's a whole bunch of stuff you almost never have to fiddle with, but lives in your program, even though you never explicitly put it there. But it's implicit when you make it. Now this stuff here, if you just override some of it has really nice function pointers inside it. And if we override the function pointer, what can we do? What is a function pointer? It's just a pointer to code. Like, where do you want the next code to execute from? So you could just point that to your code, right? That was at that time. Okay.
So is the heap executable? So like, can we put our
good
stuff on the
question.
heap and then
So
point it back to
let
it?
me clarify the model over here. We're kind of back in the mindset of like things are executable, but we're not overwriting stuff on the stack. Right? And then we can get back into the mode of having protections against this stuff. Anyway, things are now executable and everything's nice. So we could just change the function pointer to point to something that we control. If we don't do that, the way, for instance, if you have a function pointer, the way people exploit it if the things are non-executable is that you replace it with an instruction, exchange some register that you controlled for whatever reason. Maybe it was the buffer that was being used. It was an EC actually. Exchange that with ESP and then return. So now you set ESP to be something that's user controlled, and now you can just start your ROP step. Does that make any sense? So you told the program like, oh, okay, to get to malloc, you actually have to execute this instruction over here. It's the exchange ESP with some register of my choosing, or jumps into that location, right? And that means that now when you do return, you have a stack pointer that is in some part of your memory that you control, which is a series of raw pointers that are going to generate what you want. That's how we tie that together. But for now, let's just imagine everything's executable, right? And in the exercise you'll be doing on these things are going to be nice and executable. All right. So we can override function pointers. That means that whenever somebody calls a function pointer, we use these control. Make sense? So that's all about static overflows. What I wanted to talk to you about, which is a lot more elaborate, is about malloc. And for me to talk about how we overwrite things in the memory allocator, we have to talk a little bit about how it works. How many people have spent some time thinking about how malloc and free or new and delete, how that actually works? You have?
Well, when I was trying to figure out what was going on with this, I wrote some stuff in the book.
Good, okay. Well, is there something in particular you learned from this that you can share?
I just know that when you want to free some space on the heap, you use malloc. And if you want for that space to be reused or like you want to get rid of it, you use free.
That's right, yeah. Use malloc to take up some space, use free. Exactly right. So the question is, like, suppose you were tasked, suppose you're in a world where there is no malloc for free. And all you can do is you can ask the kernel, like, give me a gobs of memory. How would you implement something like malloc? Let's talk about that. So the kernel has this thing called BRK, which is just, hey, give me a whole bunch of memory, a continuous slab of, let's say, hundreds of megabytes of memory. Now, if you had the program and you wanted to be like, oh, I want to get like 24 bytes for my structure. I want to call malloc of something small. You don't want to have to talk to the kernel for those little things. In fact, the kernel is only going to give you something that's at the boundary of being like divisible by 4096 bytes, like a page. In other words, we're doing transactions here, and you're talking to IMF. Right? You're like, oh, I need some change, right? I'm going to talk to the IMF and get a loan, right? So instead, what we're going to do is we're going to create like our local bank thing, which is our malloc unit, which is something that lives in user space, and that can talk to the IMF and get a loan for some big number, and then administer small transactions built in. That's what we're trying to do. Does that make sense? So do you guys remember how the interface is? Here we are in set the heap here. We're trying to do this red segment. We're going to try to figure out how to allocate space within this red segment. And all we want to talk to the kernel about is about growing this thing here. Like, hey, can you add 500 megs to that? Can you decrease it by 500 megs? That's the granularity which we want to involve. So let me set up the exercise here. So we have two functions we want to implement. There's a thing called malloc. All we tell it is how many bytes we want. And it's either going to tell us, oh, I have no such thing available, in which case it returns null. Or it's going to give us a pointer to memory that's guaranteed to be ours to do stuff. Now, of course, when I say we're still working within the premises of a single program. So technically, we own all memory that's there. It's just that not all of it has been actually allocated, right? And when I say we, what I mean is that when you call malloc inside the function, no other function gets the same memory. You're not stepping on somebody else's toes when you call malloc. You get a chunk that's exclusively for you. And it also means that if you ask for 24 bytes, you might get something that's 500 bytes. You don't know that, actually. But it's guaranteed to be at least the number you asked, 24. Does that make sense? And then when we're done using it, we're supposed to call free. So we take the same pointer that we returned from malloc, we call free on it, and that means that we're done and it can be used for some other part of the program. Okay? So let's see, let me just take an example. Like here's a program we call here, character pointer is equal to character of malloc of, say, 200 bytes, right? And then I do something with the pointer, I can say pointer of 0 equals to, like, I don't know, 41. I'm just kind of doing some random stuff here. And then when I'm done, I call free of PTR. And from this point on, should not use PTR and so forth. Right? This is a standard C program that calls malloc, it calls free. Your task is to tell me how I would implement malloc and free so I would have this interface. And I'm soliciting assignment ideas starting now. So, how would you implement malloc and free? So the first malloc is probably going to be like, well, I need some memory to start with. So we can call BRK, the kernel. You're like, oh, here's 500 megabytes, look at all this money, look, go, I have it. And now you're like, okay, somebody called malloc of 24. What do you do? How do you administer it? It's like, here's something. It's like randomly pick something, so we find. Right. If I just do that, if I just randomly take 24 bytes here and I mark it as being in use for this guy here, and then this guy over here, and so forth, will I run into any trouble? What would I like to happen?
You'd like to use all of that stuff most efficiently.
Yeah, I want to be
You just take
efficient.
the first 24 and use that, and the next one you would take the next. Unless people are calling malloc, they're like stupidly. Like if you're like, oh, allocate me 24, and then you're like, oh, well, actually I need like 3 more on top of that, then your whole scheme would fall apart.
Yeah, so there's in fact something called realloc, which is to say like, I was wrong, I need more. Please fill up my allowance, right? Which case you need consecutive space here. But it's really just like saying, hey, allocate 24. Oh, actually, don't need this 24 anymore. I need 48, right? And then you ask, so you have malloc, free, malloc. Right? So you have a sequence of these mallocs and frees coming in and out. And somebody want to be efficient. What does efficient mean? It means that we don't want to be in the case that we say malloc, and it's like, oh yeah, no, I can give you that memory. Like, we'll check in later this year. Right? We want to be like instant. We want to be able to say like, here's your memory, because this is being called inside loops. Right? Same thing for free. We don't want to be like, oh yeah, but we're not using this memory anymore. Hang on. Right? And just wait until it, successfully like, it's now safe to turn off your computer type of thing. Right? We don't want to be waiting for some process for either free or malloc. It should be instant. So order one operation. Second thing is that if I start to like eat it like Swiss cheese, and I'm taking in just random addresses, then I'm not really using the memory very efficiently, right? I'm like, I have all these holes in between, and then I'm like, well, I just need more. Give me more memory. Come on, right? That doesn't work either. Some are going to be effective at how we lay it out. So today we're going to try to create effectively what people have implemented today in both Windows, Mac, so like BSD, and Linux. Okay? So this would be really interesting. If you know how to do this. Normally, when I teach this course, it's because people have been taking a course that talks about how you implement things like that. So they will have their own malloc implementation. And then my exercise is going to be like to take your malloc implementation and hack it to shreds. But once you're doing that, I'll give you several malloc implementations, and you'll have to hack them to shreds. And they were implemented by former students of this course. Yeah. So, here's the situation. So we would like to, at least somehow, we need to know the number of bytes that we have allocated, right? If malloc says like, oh, it was 24 bytes, it probably needs to somehow keep state to know that it was 24 bytes, right? So how should it do that? Start with. Everybody look busy quick. Oh, look, there's another there. How should we track that? Yeah, okay. Somebody texted me the answer. Okay. No, it's incorrect. So, how do we track this? Track this.
You have to trap it on the heap, and then as we add and remove from it, change.
So you'd have something on the heap that's just like, it's like a telephone directory. It says, this chunk over there, it's 24 bytes, right? And this chunk over there is 24 bytes. That's fine, and that is one design. And that's somehow that like would be very natural to do. But the thing is that now we need to somehow take into account that we have all this heap, and we are administering the heap. And we're taking memory on that heap for us, and then also for the user, right? And now we have to be careful about like, oh, I've actually used up 75% of the heap here for my own data structures, right? So it means that I only left 25% for the actual user to use. That's pathetic, right? So, and then like once I free that up, I need to now make sure that I can reuse it. So somehow I have something like the stack and the heap principle, and you need to grow in each direction. It gets really hairy. But here's the thing, is that there's nothing that says that when we allocate stuff, that we need to just say, if you ask for 24 bytes, I don't need to give you exactly 24 bytes. In fact, I could even use parts of it. So what if I just go here and I say, hey, I want 4 bytes, or 4 ints, or whatever you want to call it. So I'm going to go ahead and be like, yeah, so you wanted 5? Yes, 5? Okay, here's 5. But I don't tell you about the first one, because I kept the size in there. So now the size is a part of every chunk. Except the user doesn't know that. The user just sees this pointer here, P0, and sees that he or she has at least 4 ints of data or slots of data. But the size is stored in here. So that's cool, right? That's another way of just embedding it in there, right? Okay, so what are other challenges we need to tackle? So this also means that when I call free, how would free work? Free gets in just a pointer, right? How would you implement free, knowing this?
So it goes 1 byte before the pointer. and
That
so on.
backtrack there, just like a Michael Jackson thing. Zoom, moonworks back here. I'm like, oh, 5. And then it knows how to do sort of 5 bytes here, and it can just release it. So now here, look at the colors. We have this gray and we have this white. And gray here means allocated, right? Notice that there's some fragmentation. If I were to ask now for 3 bytes, I can't do it here, can't do it here, but I can do it here. We're not at liberty here to move things around. And that's something that's pretty peculiar. That's something that's not true for modern programming languages, where you have something called smart pointers. Here, if I move stuff around, somebody has a physical pointer to a memory address that's right here. And we can't go through the program and update it. Once we've allocated something, we're committed. So here, if I ask for 3 bytes, I cannot use these 4 non-contiguous bytes right here to allocate. I have to take it from that chunk over there. Yes?
So I remember in old Windows machines, there used to be this thing called a disk defragmenter. So would that
Yeah.
kind of just like, could you do something like that just go periodically and like just bunch things together and like change everything?
Yeah. Who has run defrag here? It's fun, right? Doesn't take any time, it's not annoying, right? Mm-hmm. Yeah. So few rants here about defrag. Yes, in crappy operating systems with crappy file systems, you can run defrag to rebalance the trees that are used for your file systems, right? This means that you do nothing else on the hard disk, or in fact on your computer while this is running, right? You have to squeeze everything there, you move all the files. Here, we're in a program, and we don't want to be in the state where like you're running your program and it's really annoying, right? It's really annoying. So now you have to stop the program and be like, okay, everyone, stop. Now we're going to like move things around. Incidentally, Java chose this design. Java has a garbage collector which does effectively this. Defrags, it has like all this reference to be like, let me just sweep through memory and see if something's not in use. Like, oh, it's not, okay, I'm going to move this around, does all this stuff. And then sometimes when it's really, right, you just like, you actually stop the world. Okay, it gets really boring when you're playing games. Anyway, so in C, you can't really do that for 2 reasons. One of them is you can't move pointers once you've committed to it, because you would have to actually go through the entire program and find anything that looks like a pointer, and it goes to this memory. And even so, it wouldn't be a safe thing to do, because something could look like a pointer if it's not. And so you have no way of going back to seeing like who has references to this. But in Java, you can. On file systems, you also have double pointers, and you have persistent state. But here inside memory, the operations you're doing of it are everything's supposed to be faster because it's in RAM. And you don't have the liberty of going back and forth and being like, okay, there's a 4 pointer, and yeah, I know it's not that. Everything is just a series of memory. Right? So defrag doesn't really hit it. Now another thing about defrag is that modern file systems don't need defrag. They are smart enough to know how to structure themselves so that they don't need to be rebalanced. They are self-rebalanced. They use a log. This is so cool, right? I thought this would be fun. Okay, so that doesn't quite work, direct balancing. But at least we know how to implement malloc and free using just these chunk sizes, right? Okay, so that's cool. So if I want to now call malloc and I want to find something, what do I need to do? So if I ask for here about, for instance, malloc 3, and this is state of memory, what do I need to do if I'm malloc? Yeah.
Find 3 bytes in a row that are free.
Okay, so I'll just scan. What do I do? Doesn't that go against our goal of being efficient, right? We have lots and lots of memory, right? We don't be like, hold on. Go through gigabytes of memory, find something. Someone want to be a little bit more efficient than that, right? What can we do?
With memory that's taken, can't you use the size that's already there? With those?
You can use the size, this size here? Oh, so you can be here and be like, well, okay, this is a tank of size 2, size 2, size 3. You can go like this, right? So your scan would be more efficient because you can just build the chunks, right? That's true. That would already be better, right? Yeah. So let's try something like that, right? So we want to be able to efficiently find a chunk of a given size, right? So instead of just having one list, like what you're describing here, of sizes, let's have several different lists. And they're going to be for chunks of approximately some size, right? So imagine you had like, we can just take examples here. Is it called? Or I can just do a notepad here. Instead of saying like, I want chunks of exactly size 17, 13, right? I can have like, list of 0, it's like chunks of size 1 to 10. List of 1 is chunks of size 10 to 99, right? So we could do something like this, 100 to 99. So what is this listing here? It means that if I start to look at list number 1, it's somehow going to tell me the next available chunk that is roughly this size. Okay? Would that make sense? So now if we call malloc of 37, what do? I go and I look in list number 1 here, like list of 1, and I just find the next chunk there that's at least 37, right? It could be that it's a size 10 and that's not good enough, but the next one was 40. So we were like, great, we'll pick that one. Does that make sense? We have lists free size stuff. And when I free something, what do I need to do? I'm sorry.
Put it back on the list.
Put it back on the list, right? Right. Just put it back on the list. That's an easy operation. And when I want to malloc something, I just find something on the list, and they're all roughly of good enough size for me, so I can just pick one up, right? And of course, I don't have to make this multiples of 10. I could make it multiples of anything else to optimize it, right? It could be powers of 2 or whatever, right? Okay. So that's cool. So we have a list of free blocks of given size. So here right now, that means that in the free block itself, we're using that space that's not currently being used for pointers. Oh. This is actually important. So one design of doing this is that we keep like in somewhere in Heap a massive array of pointers saying exactly where all the chunks are. But here we're just piggybacking on the space that we already have unused to say, this is a free block over here, it's of size 5, and the first thing here that used to be data, we're now going to recommission that to be a pointer to the next chunk of similar size. So when it points to here, it says, hey, here's another chunk that's roughly 5, it's actually 6, and so it's 6 bytes over here, and then so on and so forth, right? We don't need anything like that for the things that are available, because as soon as somebody frees them, we're going to see that, for instance, if somebody goes free here, it's like, oh, okay, it's of size 4. I'm going to go into the list that contains the things of size roughly 4 and just add it to there. Now it's on the list. Cool, huh? So far, so good, right? But suppose I did free this guy over here. Do you notice anything peculiar about the layout of memory right now? Yes.
You have a free block of size 15, but it thinks you have 3 separate
Yeah,
blocks.
it's all become like change, right? I don't have any big bills. I just have tons and tons of coins, right? I just have like, oh, okay. If I want to ask for a block of size 15, they'll be like, there's nothing here, right? That's not good enough, right? So what should we try to do? Yeah.
You could have blocks of fixed sizes where like they point to each other essentially. So like if say they want 150 bytes and
Mhm.
each block is 50 bytes, well, okay, let's say 60, so we have room for pointers.
Mhm.
You would then give them 3 of them, and the first one at its end would point to the next one. So even though they're not strictly contiguous, it would be 3 that are connected together.
So which means that they're contiguous, right? They're connected like that. Because we can't be like, oh, here's 15 in like 3 different continents, right?
Yeah.
It has to be actually consecutive. So, but the fact that we have 3 contiguous free blocks over here for small size means that we could also instead have one big one somehow, and rather divide that big one up. For instance, if we have a big one and somebody asks for 3 bytes, we could just take 3 bytes and then leave the rest, put it back on a free list, right? But how do we ensure that we merge up these things? What would be a good mechanism for it? See,
When you free it, if the block before it is free or if the block after it is free, just combine them.
that's beautiful, right? Is that enough? So in other words, like if I'm freeing this guy over here, and then I just check and see like, hey, is the guy in front of me, is that guy also free? What about this one over here and after me? Oh, what's free? Let's make a mega chunk here. So it's what, 15, right? Right? But don't I also have to check what if the thing's 2 in front of me is free, or 2 after, or 3 after, or something like that?
Wouldn't that be done when the one before you is free?
Exactly right. We only have to check before us and after us. The invariant that we're maintaining here is that there never are 2 consecutive free chunks. Remember, because if there were, then at the time the latter of them was free, they should have checked the other one and consolidated with it. Right? It's a consolidation. So in other words, we tried to maintain contiguous free chunks as being as big as possible. And then rather, when somebody asks for smaller things, we just divide it up. Sounds good, right? So far, we're pretty close now to what things are. One of the things that we did, though, was that we get a free to this point over here. And we mentioned that, like, okay, well, we want to know if the next one is free, and that's easy. We say, like, okay, this plus that number over here, that's the next chunk, okay, and that's of 6 bytes. But how do we check the previous chunk? What would we need to do, given this design right now? To find, because this guy here could not be 5, but it's 5,000 or something. Can we just scan backwards and then look for a number that looks good? And that's probably not going to apply, because there could be anything inside those chunks, right?
Yeah.
We could have a double linked list. Why not, right? Right? I told you the first rule of government spending, right? Yes. 1 by 1, 1 by 2, twice the price. Right? 1 and 2 pointers, right? So, stop. Help. Stop. Okay. So we could have double linked list. Is that enough? So what does the double linked list do? Points backwards, right? So we can go back and forth on the free list, right? But hold on a second. We're not using the free list here because this is mega size 4, but this could have been 5,000 and this could have been 9,000, right? 9,000. So it could be that these are in totally different free lists. So we can't just find this chunk over here because we're looking for something that's like spatially look at the same spot. But the list could be all over the place. So we need some way of getting backwards. That's the point, yeah.
You know the previous allocated chunk of memory, just go to there and you know the length that you
But
put.
how do you know the previous allocated chunk of memory? How did you find that?
Shouldn't malloc maintain the list of
Well, but the list, but then you have to scan the list now. And you have to find the address that's closest to the one you have, and that takes some time. The list could be millions of chunks. Right? Now, you're right, you could go through some free list or something like that, but it's just, there's a more efficient way of doing things. And this is the Donald Knuth trick. Imagine you're walking this direction. What's nice here is that at the beginning of every chunk here, there's the size of the chunk, so it's easy to go back. Now imagine you're walking in this direction.
So that's what I was playing too.
Ah. Uh-huh. Instead of just having a header of the size, also put it as a footer. Right? Then it's symmetric, doesn't matter which direction you're going. So you keep the size in two places. Oh, nice. Now it's very easy to consolidate back and forth, yeah?
Would you have so there versus 4,
Mhm.
and instead you have 5, and then you.
Yeah, you actually allocate 6, and then you say 4 or 6 or whatever number you want this to represent. If it's data or if it's the actual size of the chunk, you would have it here, and then you'd have the data, and then you would end it with another. All right? Nice. Okay. So this is what we've come up with. Yeah, you have a question.
I guess I'm slightly confused. Are we looking at these as like nodes? Because you mentioned something about double.
Yeah, there's two things going on here. This is the contiguous kind of scale of memory. And then somewhere to the side, we have this kind of logical linked lists of things that are free. I'll get to it in the next slide. But we're using the part of the memory that's on the that's in a free block to put all similarly sized free blocks together. So they can be all over memory, right? There's no reason for them to be contiguous. So first we want to get rid of the contiguous part, the spatial thing here. And then we want to be able to say, like, efficiently find me a block of similar size anywhere on the heap. Okay? So when a thing is allocated, when a chunk is allocated, this is what it looks like. Is that the user gets to see this green address over here, which is of some particular size. But what we've done as malloc is that we put a header on it, it's called size, and also a footer. And when we free it up, what we're going to do is that we're going to add it into this linked list of roughly the size of this chunk. And we make use of what was previously the payload and is no longer in use by adding 2 pointers. So next and previous part of some linked list of what's called the free list for the node, for the chunk. And we, of course, also maintain the size here so that you can traverse memory sequentially. Does this make sense? And we maintain the invariant that there are never 2 free chunks contiguously in memory. They're always consolidated first. So far, so good? Now, there's also this thing here called A. It's a little bit here. It's the very end of the size. All it says is, was this chunk in use versus free? Right? So that when you're going and you're free and you're checking if the next chunk is allocated, all you have to check is the 8-bit on the following chunk set or not. The same thing when you go backwards and you look at the footer of the previous node, is the 8-bit set? If it's allocated, well, we're not going to do anything. If it's not allocated, meaning that it's actually in use, we're going to consolidate with it. Make sense? Cool. So here are these free lists that I was talking about. So the idea here is that we track, and this is the logical way, we track a doubly linked list of all chunks of similar size. Right? But in reality, it's going to look physically something like this. There's going to be a chunk here called A, of size 4, and it points to the next chunk, which is B, which is also size 4, and that could then point, that points to another block C, which is over here, and it's actually prior to it in space. We don't know how things are going to be laid out physically, but it could be all over the place. And then we can also go backwards. For instance, if I just moved to A, I can go backwards to, from B back to A here. So it's a doubly linked list, right? So far, so good, right? Cool. These are called forward links and backward links, or prev links. All of this will become very important as we start to exploit this, right? Remember that we're not making stuff, we're breaking stuff. So here's the coalescing, right? How do we get big blocks back? And we already talked about immediate coalescing. Here's P, and it's being freed, and I realized that, like, well, actually, this thing that was free after me, these 2 bytes over here, well, it could just be a part of this big chunk there. We don't even have to overwrite this 2 over here. It's gone. It's just a part of payload or X payload. Same thing going the other way. Right? So now, when we free stuff, here's what we need to do. Well, we need to, we've just freed this yellow region over here. We need to check the chunk that's ahead of us, before us or after us. And we coalesce with it. And if we don't, what we're still going to do is that we're going to add this chunk to a free list. And the way you add it to free list actually matters in terms of how much fragmentation you get in memory. We're going to use a LIFO policy, last in first out, and that's going to be fine. So there's some root here that says the first thing on this free list over here is this chunk over here. And then this thing here points over to the next chunk that was previously the head, and so forth. And then there's a backward pointer. So we actually have to change a few pointers when we do this, right? Okay? So suppose now we're in the case where we're calling free, but in fact, the previous chunk is already free. That means that the previous chunk is already embedded in some free list, right? So what must we do? But to remove that one from the list, because it was in the list of things that were size 4 or something like that. Now it's going to be a part of our big chunk here that's going to be in the list of size 8. Right? It's going to be a different free list altogether. So we remove it from the list, which means that we move this point over here, and that point over there, just like we only regularly. And then we take the head of the list that we need to go to and make that point to our new big consolidated chunk. And then we point on to what was previously the head there and make that one point back to us. Ta-da! And if we have the case where things are behind us, again, we unlink here on the right-hand side, and we add us to the list. And if it's on both sides here, we may have to unlink each of them. We have to unlink the chunk that's ahead of us, unlink the chunk that's successive to us, and then after coalescing, we create this mega chunk over here, and we point it right here. Sounds good? So far, you've effectively implemented a perfectly good implementation of malloc. It's cool, right? Took only like 20 minutes to understand. So actual implementations of malloc are several. They're subtly different, but the most common ones are something like Douglas glibc, which is what we use in Linux. So inside your libraries, when you call malloc, his implementation is the one we use, and that's the one we're going to talk about. There's something called, I don't know how to pronounce this, not obscenely, PHK, we'll say, which is used by BSD and Mac, and so some others. There's a tree-based one used for Solaris and Iris, which are operating systems that I'm sure you have never heard of unless you've logged onto one of the department machines. It's just kind of like logging onto a museum. These are really, really old school operating systems that are dying. And then there's the RTL Heap, which is pretty similar to the Linux one, but has a few more bells and whistles, and that's for Windows. And so we're going to focus on the first one, but all the ideas apply equally elsewhere. So in Douglas glibc, it's almost exactly what we described, except instead of having a header, instead of having a footer, we kind of view it as a part of the header. So the first thing in the chunk is the size of the previous guy, and then there's the size. So it actually looks the same in memory. It's just a question of what you call the beginning of the chunk. It's the only difference, right? And there's another bit here that just says, did I actually get this chunk by calling mmap, which is a part of calling brk. And it's something that we don't really think about here. The rest of it, exactly the same. And when things are in use, we just don't have the next in the break. All clear? Good. So let's look at the actual implementation. Ready for this? So this is just copy pasted from the actual code. So here you're looking at system code. What's going to happen? There's some purple code here. It's not purple in the source. You're welcome. The purple code here is trying to deal with things that are going backwards. So it's trying to see, hey, the thing that was before me, this is a part of free, was that free or not? This is checking, was the previous one in use? If not, it's free. And I'm going to try to figure out how big it was by looking at previous size. I'm going to find the chunk, so I have a little macro called chunk.offset, by just looking at the previous size and just going past the previous size. And then I add that to my size, because now it becomes bigger. And then there's some stuff we don't have to care about here. The last remainder, well, then we call unlink, which I'll put here in maroon or some sort of weird red color. Okay? And then we do the same thing when we go forward to see, is the next one in use? If it is, we add that to our mega chunk size now called SC. Last remainder we don't care about. Otherwise, we're going to unlink the next chunk from its free list. And then we set the head. Okay? And then everything gets set here. We now say that, like, well, now we have a chunk and it's not in use. And the previous one, yeah, so we put here, we set the head and that's the size and it says the previous one is in use because we know that it has to have been in use, otherwise we'd have two free ones in a row. And then the previous size is going to be ours, we're just putting the header right, and then this is just for the process. This is the actual implementation of malloc. So you can kind of, you can look at it and into it and see that you kind of understand what's going on. Let's look at the macro called unlink. In the unlink, it takes in backward pointer, forward pointer, and it just says, hey, to remove something from a list, remember we have to follow how to remove from a double linked list. You have a chunk, I'm the chunk right here, okay? And I'm removing myself from the list, so I have a backward pointer and I have a forward pointer. So I have to kind of move to this guy over here and tell its forward pointer to point to my forward pointer. And then I have to do the same thing. I have to go forward and then tell that backward pointer to, instead of pointing to me, to point to my backward pointer. This is what we're doing here, right? So forward pointer's backward pointer is now ours. Backward pointer's forward pointer is now ours. And so forth. Makes sense, right? I've shown you this now in excruciating detail. Why? Because we are going to mess this up, right? The situation is that you have programs, and just like before in a stack, you have insecure functions like string copy or something. So the situation might be something like this. There's a chunk called P, it's only of size 24, and somebody copies stuff over it, something that's too big. Oh. Now let's think about this design of ours. When we created this malloc, we weren't thinking about security at all. Should we have? Is there anything there that's unsafe?
You're not deleting the information. You're just removing the pointer. So all of the stuff that you're storing in this chunk of data is still there. So if it's sensitive data, someone can just search through and find it.
Okay, so maybe read something you're not supposed to.
Yeah.
But is there anything more than that? We have data now intermixed with bookkeeping information, with our control data, right? It's not a return address, so it's nothing just as blatant as that. But there's stuff in there that is actually very useful. What specifically can we do in this circumstance?
You make it seem like certain blocks are free when they're not.
Ooh. Why would that be useful?
It would think it's allocating memory for a buffer, but in reality you're overwriting some data that's actually important.
That's a very good point. This is actually called a use after free vulnerability. So sometimes you can trick a program into thinking something was previously free. So now two parts of the program are allocating the same chunk. Usually one of them is under your control and the other one is just under somebody else's control. And that can mean that you can kind of camouflage what's in that buffer. But there's something a little bit more nefarious at work here. A return address on the stack is pretty much like a pointer, right? It points to where we want to resume execution. We also have some pointers here, don't we? What are those pointers? So forward and backward pointer, right? For free check. So imagine that somebody calls now free of P. We could also analogously have a similar situation where somebody calls free of Q, where Q is the successive chunk. Okay? What's happening? Suppose this is our, what we call malloc, this is the chunk we were given. There's some header here, and then there's the data. And there's 24 bytes of data. And I now overwrite more than 24 bytes of data. What damage can I do? Short size. What would that do? Who specifically uses size right now? You're still in the string copy line over here, but then later somebody calls free of P. So free of P is going to try to see like, hey, is the next chunk, is that allocated? How does it check that? Going slower. Huh? To check some part of the size thing here. What do I check? Hey, I try to see if it's in use or not. But I controlled that information, didn't I? So I might say that, well, actually, it's not in use. Yes, it's into coalescing. Yes. Right? This is very exciting for this crazy person that I'm debating. It's not me. Right? Why is this interesting? Because if something is not in use, if it's free, and I'm freeing this one here, then I want to create one big mega chunk. And when I create one big mega chunk, I expect this free chunk here to have what in it? Pointers, that's right. There's going to be 2 pointers here, which is the what free list does this thing Q here belong to, right? Except during my string copy, I overrode that too. In fact, maybe there weren't any pointers at the begin with, but now there are. Right? Right. Is it about seconds, yeah? Okay, so here's my big blob of data, right? This is what I'm barfing into the program. Okay? And so here's data, and I can pretend the second block is already free. And if instead, if this whole thing was about freeing Q, I could also overwrite this prev size A here and pretend that P was free. Right? So what if I put something like this? What if instead of prev size and size, I just put in some number like this? Why would I put in a number like this? Why not just like 0.00024 or whatever? Well, free is going to look at these sizes. In fact, free of P is going to look at this size over here. And it's going to try to add to its current pointer that size. And then it's going to look at that as being, oh what?
Well, that's going to be negative. So,
Yeah, it's -4, right? And in fact, it doesn't much matter what is here, except the A bit has to be unset, right? We just want this not to be allocated. And the reason we're putting F's here instead of zeros is because we can't put zeros. Right? So just put whatever in here. And if there are checks inside malloc of seeing like is something plus the size of the other one, is that still a valid address? Instead of that segmentation faulting, which is putting random stuff in here, this is pretty much guaranteed to be safe space because it points to this, right, or whatever number you like. But crucially, we're putting 0 into the A bit, which means, hey, this thing, it's free, which means that we have a next pointer and a proof pointer. Ta-da! That we put in there. And now we have to think a little bit hard. What would we put inside a next and a prep pointer? Remember how we were dealing with next and prep pointers? We were calling this unlink macro, right? I can hear my heartbeat. There's no noise here. It's eerie. Thank you. Anything else? What will we put in there? Thank you too. Next to prep. What do we put in there? We're trying to hack this program, remember? We just had an overflow, we found this awesome thing, like our heart is pounding, we're like, oh, we're attacking this thing, we're gonna break it to shreds. We've overwritten the data, we've overwritten all this stuff, and we put in a fake allocated bit over here which says that this thing here is free even though it never was, doesn't matter what it is. And we say that there's a fake next pointer and a fake previous pointer. Someone want to assume control of this program, right? We'd like to execute shell code, right? We don't have any return addresses to override, but we do have this next and prep pointer. What could we do with that?
It's probably wrong, but I was thinking access like it allows you to have reference to other locations.
Yeah, so we could put it somewhere and pretend that's somehow part of our linked list or something like that. Somehow, this is definitely useful because we're writing something into memory at the locations of our control, right? We control exactly what these locations are, and it's going to write to them as a part of the element, right? That can't be unuseful. So let's figure out what it is, right? Or if we want to do the free queue thing here, then we're setting this block up here to be the previously, the one that's already free, all right? So let's look at the unlinked macro exactly here. So we have next and prev, and look at the color coding here. Purple and green, so amazingly matched, right? So we're going to take this pointer, this is our forward pointer, this is the next, and we're going to get a copy of what's at PBK, so BK now becomes just prev, and forward becomes next. So now we're going to do this thing here, forward, like if we follow the forward pointer, we modify its backward pointer to become this value. And what is happening here? This is effectively what's happening here. If we look at the assembly underneath. The unlinked macro is going to be doing this. It's going to say, I look at next here, and I add 12 to it, which is effectively like this next FP over here. So I follow that one, and I write into it the value of next BK, which is our backup one, or our prev address. And here we take the prev address, we add 8 to it, to find the right address within the structure, and we put the forward pointer into it. So what could we possibly do here? We can write down our new numbers. Yay! Okay, this is just the opposite. Okay, when you go home, please make this awesome when you look at it. You're like, oh yeah, that's right, this is so cool. You're on your treadmill, you're gonna like fall off, right? It's gonna be awesome. Okay. So this is an actual exploit against it. So what are we doing here? What we can do in here is that we can put in a fake next pointer, which is just the pointer we want to overwrite, which could be the address of a return address. right? Somewhere on the stack. And then, what do we want to shove into it? Well, we just put in the fake address, which is just the address of our shellcode. That's it. So we kind of linked in, like this obscure, our shellcode was linked into like our return address. Is all kind of really morphy. But really, if you just look at the memory addresses we're doing here, all we're saying is that take this, in the green here, the location of where I have a return address, and it actually is 12 bytes before I have that. That now contains the address of my shellcode. Ta-da! Just that line does everything we need. Now what's peculiar here is that then also we have 8 bytes from where my shellcode begins. I get the return address. That's a little bit backwards, isn't it? Let me draw this, just so it's clear here, right? So we have memory here somewhere, okay? And let's say that this is the stack, right? So on the stack, we have also the stuff, we have buffers and all stuff. And at some point, we have here a saved EBP, we have a saved EIP, and we have some other stuff, right? And let's say that I know the address of this. This is OX. This is like some stuff here. This is OX, FF, FF, F0, C8. And this is then CC. And this is then D0. Okay? And so forth. Yeah. Bless you. So this is somewhere in memory. And then somewhere else in memory we have our friends OX 90, 90, 90, 90, 90, EP1F, whatever, right? So shellcode. Let's say that this 90 address over here, this is an address OX FF, F, DE, AP. Now, what do I do with this macros? What is FD here? So I'll put in an X pointer here, and that's going to be one of these addresses, and the prem address is going to be the other one, and which one is which? And what will happen? It doesn't matter, because it's kind of symmetric, right? So I'll just put one or the other. So tell me an address that's useful. Of the two that are written on the board, pick one. Thank you. Okay, FF, dead. And then here. Okay, what was it? F0, C8 wasn't it? Yeah. Okay. And now let's look at what the macro does. So the macro now says at address F dead plus 12. Just to make it serious, let's not make it dead. Let's make it D80. Just so arithmetic works a little bit better for us here. Plus 12 becomes the address of what the macro pointer is, which is F0C8. Okay, so what do we do? What happens to memory here? No other color. Oh. I found the smorgasbord of chalk. Okay. The trove. What happens? Tell me what this is the first thing that happens, right? So I write what to where? And this is 0. Where do I write to? Anyone? I'm writing to this address here, plus 12. So 12 bytes from where this started here. So here's 12 bytes forward, 0. Here, all of a sudden, I write 4 characters. And the characters that I write are what? FF, F0, C8. Ah, this is terrible, right? I just overwrote my NOP slab. So an ops that's going to execute 9099 and it's going to get some address and it's going to crash, right? That's bad. But at least on a redeeming note, we also have this right that happens. OXF, the other address, F0C8 plus 8 becomes what? Zero. And what does that look like on the picture? That means that I take not this stuff over here, but 8 bytes from it. So here is 0, here's 4, here's 8. Ah, I overwrote this part here. So I put in an address that was 8 bytes before where I wanted to go, right? So this becomes now F, D, E, A, 0, which is here, right? If this was the only thing that happened, this makes us really happy, right? This would just solve our problems and all our woes would be done, right? We'd hack all the money, we'd retire, okay? But this thing here is terrible, right? It killed our shellcode somehow. Any remedy that we could have? How could we fix this? Can we still make do? Somebody just dumped this here onto our shellcode, like a 4-byte address. Yeah?
Could, like, right before that address, you have a jump instruction to go a couple bytes.
Oh, I like the way it's, so instead of having 9090, we could just have like an EB, which is jump near 16 or whatever. Right? Then we execute, jump, execute shellcode. Right? So in fact, our NOP sled is probably going to be closer to being like EB10 or something like that, right? And then we have to be careful to have some NOP sled here so we don't jump into the middle of our shellcode, right? So have some cushion. Make sense? Cool, huh? So look at the exploit now. What do you notice? Ha ha ha. Here's our shellcode, and it has an EP12 in here, right? And here's our address of return address, and here's our pointer to override the location -12. Because of this stuff here, we had to move backwards a little bit. Does this make sense? Any questions about this? I was going to show you a demo, but I have 2 minutes. Yeah, I would also drop myself. 2 minutes. Cool, huh? And WTF here is because of the jump that we had in here, which we already did. Now this can also come up when you're calling double free. So if you want to protect against this, you have to make sure that when you free something, you set it to null and make sure nobody else is using it. There was a bug like this in zlib, which is the thing that compresses stuff, which everybody uses. So that means that the path, like the Mars rover, is susceptible to exploitation. Please don't hack the Mars rover. You would be the worst person in history to do that. So, oh, we can't access the Mars rover, and then the last side is like, because somebody hacked it and put in like a website that's like, I hacked your rover. No, not cool, right? Yeah, the language is auto-generated and ensure that the structures are only called once. And so the summary of what we did today is that there's lots of vulnerabilities that can that are of the nature where you're modifying things on the heap. This is very common today, these types of bugs. Most of the Internet Explorer vulnerabilities that come out every day involve some sort of heap magic like this. Static overflows can also be exploited. They're not very common. I explained how malloc works, but now you know how malloc works. Yay! And it can be triggered by things like double freeze and even by the frame pointer overruns that we talked about before, because now you may be calling free of a different address, and so it could be something to control. Any questions before we close? We'll try to have a demo next time if that's suspect that might be helpful. Cool. Okay, so office hours at, what did I say, 2:15 to 3, or? Second? I hear different numbers. I'll just confirm this myself. It's at 3:30 to 4:15, yeah. In my office. Okay, so if you want extra office hours, otherwise it's due tonight at midnight, and good luck.